right, now we're going to look at a proof of the bibostability theorem. So theorem 15.1 basically said we have bibostability if we have this condition satisfied. And notice it's if and only if. So in order to do the if and only if, I actually have to prove two things. I have to prove that if my system is bibostable, this condition is satisfied. I have to show that if my system is if this is satisfied, my system is bibostable. Okay, so I have to prove two things. So first, let U be in L infinity. That is, it's bounded. But it's an arbitrary element of L infinity. And so we have this output given by this expression, and y of t exists in r-dimensional space. The elements of this vector have the magnitude. So if I look at the individual elements, I can break this up. So this, by looking at an individual element now, we're actually kind of looking at a row of G. Okay, we're looking at a cross section of the matrix, of the capital G matrix, which is just a row that we're looking at that multiplies U. So the absolute value here is given by this absolute value. Okay, so the ith row of this is basically all of this, and we just take the absolute value. But this absolute value of the integral of the sum, I can take the absolute value inside, and I get a less than or equal to, because these quantities could be negative, so sometimes you get adds and subtracts. But so in general, all of this is less than or equal to all of this, because we've taken the absolute values on the inside. Now, if the G's are all positive and U is all positive, then I can get equality here. So it's possible to get equality, but in general, I will get strictly less than in general. But anyway, well, I guess in general, I get less than or equal to. So I have this relationship. And now I'm going to take the maximum value of this vector. Okay, that's really the infinity norm of this vector. That's less than or equal to this quantity. Okay, the maximum over I of this. So I've looked at all the rows, and now I'm looking at the maximum of all of those. I get this. This quantity is less than or equal to this quantity, where in the integral, here I have uj of tau. I can make this not a function of uj by looking at the fact that this value at any instant in time tau is less than the infinity norm, which is taken over all time. Okay, so I get this inequality. So I could get equality here if this function were a constant value at this value. So I could actually get equality here for a particular u. But in general, I will get less than or equal to. So I have this quantity here. And so the infinity norm of of y is, so this is actually the infinity norm at time t. And so the infinity norm over all of y is the infinity norm for each value of time all the way out from the time equals infinity. And so that's the supremum over all time of this quantity, okay, which is less than or equal to, so notice I have this quantity here that is this, okay. So notice that at any given instant in time, I have this quantity, but notice that this function here, I can change the limits of integration and get this. So this, now, when I integrate with respect to time, is independent of time. This quantity is actually independent of time once I've integrated with respect to time. So this is just a constant, okay? And I have this inequality. So we've proved this direction, okay? Now we're going to do the other direction. Suppose now that this quantity is infinite. And we're going to look at the scalar case to start off with, and the general case will be apparent. So suppose now in the scalar value, so because we're looking at a scalar function, we can eliminate the sum and we can eliminate the max because we just get this. We only have one value. Suppose that this is infinite. So we now choose an arbitrarily large m. Okay, so that means there exists some value of t such that this integral is greater than m. It has to be, otherwise the limits from minus infinity to infinity, which are larger, wouldn't give you infinity. Right? So I'm just saying I can always find t such that the interval gives you an arbitrarily large integral. So now we're going to consider this input. U is equal to the sine of g of minus t. Okay, sine of g of minus t, and we use this because of the fact we're going to use the convolution, and so this kind of helps us with the convolution. So this is just a function. The signum function is 0 if the argument is 0. It's minus 1 if this is negative, and it's positive 1 if this is positive. Okay, and it's defined here over the interval between it's defined as this sign between the magnitude of, between the times of minus t to t. And so because I'm looking at the sign, this is either 0, 1, or minus 1. The infinity norm of that signal is 1. However, it's chosen such that when I multiply these two things together, I get the absolute value. That's why it was chosen. Okay, so all of this boils down to this, but I know that this is greater than m. Y at time 0 has magnitude greater than m. Therefore, the infinity norm, which is the supremum over all time of y of t, is greater than or equal to y at 0, which is greater than m. Okay, implying that we can find a bounded input, that is, um was bounded, that will give an arbitrarily large output. So if this condition is satisfied, then I can find a bounded input that gives me a large output. So that's showing my system is not bounded bistable. And so that is the proof. Stay tuned for the practice problems.